Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 32. In this particular lecture, we will continue our topic, that is saline water intrusion in coastal aquifers. And in this particular lecture, we will cover our previous topic, that is Bodon, Ghyben, Hergberg principle, and basically we will continue from our previous lecture. And second topic, we will cover analytical solution of saline water intrusion in coastal aquifer. So, in our last lecture, we have seen that if we have one phreatic aquifer, this is basically impermeable bottom, and this is the location of ocean with our z axis pointing upward, and this is the location of interface, that is interface between salt water and fresh water. And we have groundwater table located at this position. This is groundwater table. So, let us consider any arbitrary section in which this depth below ocean level to the position of interface, we can denote it as xi, and head above ocean surface, that we can denote it as HF, and corresponding head in ocean we can denote it as HS. We have seen that with our assumption, that is Ghyben-Hergberg principle, we can express this xi in terms of HF as HF rho f by rho s minus rho f into HF. In this particular derivation, we have assumed that our salt water wedge that is basically stationary or stagnant. With this assumption, we will continue our derivation for saline water intrusion in different coastal aquifer formations. That is, first one will be confined, then unconfined, and for oceanic islands. So, let us consider this ratio rho f by rho s minus rho f as delta. So, with this assumption we can continue our derivation. So, first of all, let us see that how to use this Bodon, Ghyben, Hergberg principle in the field to identify the salt water intrusion in coastal aquifers. So, with this with Ghyben Hergberg principle, it is possible to map the salt water freshwater interface So, what are the steps for identification of this saltwater freshwater interface? So, first point is that network of shallow wells are developed for observation of water table height. So, first of all, we need to install some good number of piezometers in the field to identify the location of groundwater table locally. Next thing is that we can use contour plotting for this groundwater table height distribution. So, contour lines showing the fresh water head HF are drawn using some interpolation method. What are the interpolation methods we can use? One interpolation method may be kriging or inverse distance weighting method we can utilize. So, for example, we can use kriging or IDW or any recent techniques for plotting our contour lines for the fresh water head HF. Then the interface depth xi, which is a function of x and y, is represented by the same set of contour lines and this is drawn within the plotting. And fourth one, the location of aquifer bottom which is again function b x y is found from geological maps. And the final one, the intersection of these two surfaces, that is the intersection of the two surfaces xi x y and b x y is sought, which represents the saltwater toe location. So, with this method, let us say we have our coastline like this, which is coastline, and this is our ocean, and with dotted lines I am representing the freshwater equipotential lines. These are basically freshwater zone, these lines are freshwater lines, and the location of toe, that is the intersection of two surfaces, may be located as this. So, this is basically location of toe. So, for this particular location, salt water has entered into coastal aquifer. So, salt water invaded zone. So, we have salt water invaded zone, then we have fresh water zone, and these are our fresh water equipotential lines. So, using Ghyben-Hergberg principle, we can easily identify the toe location in the field. However, for complex geological formation and non-stationary interface condition, this is not valid. Ghyben Hergberg principle considers stationary saltwater wedge assumption for its derivation. However, in complex geological conditions, we cannot directly use that assumption for practical modeling or practical use. So, next thing we will try to find out the analytical solutions for our coastal aquifers. So, for analytical solutions, for stationary interface. So, basically for these solutions we will utilize our Ghyben Hergberg principle, and we will try to see the simplified analytical solutions for simple geological conditions. So, first thing, with this analytical solution, what we can do? We can identify the shape of the sharp interface, Next, we can find out the relationship between the extent of seawater intrusion and flow of fresh water to the sea. And why this relationship is necessary? This relationship is necessary for taking aquifer management decisions and sustainable yield identification for coastal aquifers. So, this relationship is necessary for aquifer management decisions or for identification of sustainable yield of a coastal aquifer. So, we will use certain assumptions for our derivation. So, what are these assumptions? First of all, we will consider that aquifer's bottom is horizontal. So, aquifer bottom is horizontal, the flow is assumed to be everywhere perpendicular to coastline. with a stationary interface. That means our fresh water is moving, but sea water is stationary. And we will consider that sea water wedge length L and one important assumption is that Dupit's assumption of essentially horizontal flow is valid. Dupit assumption of essentially horizontal flow is valid. So, let us consider a case of a confined aquifer, and for this condition we will try to find out the nature of interface. So, interface in a confined coastal aquifer. So, interface in a confined coastal aquifer. So, let us draw the conceptual thing. We have horizontal bottom, which ensures the horizontal flow in the aquifer towards sea. So, thickness of this confined aquifer is B. Again we have the interface. This point T or capital T is called as toe location. Then length of this wedge that we have already assumed to be L. Then location of sea surface or ocean surface, we have this, and location of this groundwater table is this green thing. So, for a particular location we have three different distances. First one we will denote it with xi. Next one, this is constant depth between ocean surface and the aquifer top, that is B, and this HF is the freshwater head above ocean surface up to groundwater table. So, we can consider this zone as fresh water zone, and this one is basically salt water zone. So, with this configuration we can consider that there is horizontal flow which is occurring from aquifer towards the sea, and our x axis starts from this toe location towards sea. So, with this fundamental assumptions and configuration, we can start our derivation. What is this q f naught denoted in this position? This is the difference between the total inflow to the aquifer through its right side boundary and the pumping from the aquifer in the aquifer strip. To the right of the point T or location of toe. So, next thing in this particular case, another assumption is there, that is B is much lesser than our wedge length, and B is the thickness of aquifer. So, using our Ghyben Hergberg approximation, we have this HF is the fresh water head above ocean surface up to this groundwater table. So, we can express our this xi plus b, that is the distance below ocean level up to interface, that we can denote it as xi plus b equals to rho f by rho s minus rho f into h f, or in simplified form xi plus b equals to delta h f, or h f we can directly use it as b plus xi plus b by delta. So, for this small configuration we can say that our freshwater zone, we have flow which is K f, or we can write it as basic equation of fresh water flow, and this is 1D and only horizontal flow condition. We have Kf xi x dh x by dx equals to constant. What is this constant? This is q or flow at location x equals to 0, which is equals to q f naught. So, what is this? This is basically our flow or Darcian flow is equals to the flow which is coming from right hand side boundary, and basically we have seen this is the difference between total inflow to the aquifer from the right hand side boundary and pumping from the aquifer. So, using this thing, we can write, again we will just write kf psi x dhf x dx equals to q f naught. For this particular situation, now we can use our Ghyben-Hergberg principle. So, we can replace this HF with xi plus b by delta, or kf xi plus d by dx b by delta equals to f, or this is kf by 2 xi d xi by dx equals to q f naught, or this thing we can directly write it as I square dx, and the right hand side will have delta q f naught by k f. With this we can use integration. So, from integration we have I square equals to 2 delta q f naught by k f to x plus c, where c is the integration constant. Now, if we have x equals to L, then this psi value is 0, which implies that C is equals to 2 delta q f by k f into L. So, final equation we can write it as this xi square is equals to 2 delta q f by k f L minus x. So, important thing is that we have considered our coordinate system from toe location towards left. So, if we have x equals to 0, that is at the location of tau we have xi equals to b, which is again b is the depth of the confined aquifer. So, this implies that we can write it as b square 2 delta q f naught by k f into L, because x equals to 0. So, basically this particular relation relates with our depth of the confined aquifer. This is del is the density ratio which is used for Ghyben-Hergberg principle. Kf is the freshwater hydraulic conductivity, Qf as we have defined in our assumptions, and L is the seawater wedge length. So, this is somewhat parabolic in nature. So, we can say that saltwater interface in confined aquifer is parabolic in nature. So, next thing we will start our interface for interface in a phreatic aquifer. So, in this phreatic aquifer this is also our unconfined aquifer, unconfined coastal aquifer. Again we can draw our basic configuration for the problem. We have horizontal impermeable bottom, this is the location of ocean, and location of interface can be denoted with this red line, and this is T or toe location with salt water and fresh water thing, and this is width B, which is depth below this ocean surface level up to impermeable bottom. Again we have this groundwater table which is phreatic surface and we can assume some constant recharge rate n So, with this height of groundwater, fresh groundwater table above ocean level is HF, and below this ocean surface level till the interface we have distance xi, and saltwater wedge length, this is again L, and our coordinate system we are assuming from the toe location towards left, and we have again this q f naught, which is the difference between the flow which is coming from right side boundary, and this is the difference between flow and pumping. So, with this situation, this is H s, and this precipitation rate or recharge rate, this precipitation rate, we can consider it as N. So, within this interface, if we consider one small elemental portion, then we will see that for this elemental portion, we have this is N, which is recharge from the top, and Q F is a flow coming to this strip, and Q F plus dQf by dx into del x, this is the distance, the flow which is coming from left boundary and which is going out from which is coming from the right boundary and going out from the left boundary. So, if we do mass balance for this particular configuration, then we will see that QF minus QF plus dQF by dx into delta x plus we have n into delta x equals to 0, or we have situation where dQf by dx, this is n or 0. So, if we use our Darcian flow conditions, then we can easily see that this QF is basically minus KF into HF plus xi into dH by dx. So, this QF at the right hand side boundary, we have this value QF is equals to QF naught. So, at this right hand side boundary, QF at x equals to 0 equals to QF naught, or we can say that minus Kf Hf plus xi dH by dx equals to Qf naught. And now if we apply our Ghyben Hergberg principle, we have xi equals to delta plus Hf for unconfined aquifer, or Hf is equals to xi by delta. Now, using this Ghyben Hergberg principle relationship, we can simplify our basic equation as this minus Kf, this is xi by delta plus xi, and this is d by dx xi by delta, or we can say that Kf 1 plus delta by delta square into 2 xi d xi by dx, this is equals to Q f naught, or we can simplify this particular term as d xi square dx x naught equals to 0 sorry 0 minus 2 Q s naught f delta square divided by K s 1 plus delta, K f 1 plus delta. Again, from our fundamental relationship, that is we have derived, that is K Q f dx n equals to 0, and in this one if we substitute Q f, then we will get d by dx, which is minus K f H f xi d H f dx plus n equals to 0. This is our relation number 1, our 32.1, let us denote it. And from this one, if we substitute our Ghyben Hergberg principle relationship, so Kf, again this is 1 plus delta divided by delta square dx plus n equals to 0, or we can have a relationship where this d by dx xi square dx equals to minus n 2 n delta square divided by Kf 1 plus delta. So, from this one we can derive this square x equals to minus 2 n delta square k f 1 plus delta x plus C 1. So, from our relationship from 32.1 we have seen that d of xi square dx at x 0 or x equals to 0 x equals to 0, this value is equals to 2 q f delta square by k f 1 plus delta. So, if we utilize this thing for our case, then we have C 1 is equals to minus 2 q f naught delta square by k f 1 plus delta. So, finally, this particular equation can be written as two q naught f delta square k f 1 plus delta. So, again integrating this one, we will get xi square equals to minus 2. So, 2 will cancel, this is x square. So, we have n delta square k f 1 plus delta x square minus 2 q f delta square k f 1 plus delta x plus C 2. This is again one integration constant. So, if we have x equals to 0, we will get xi equals to b. So, with this one we can get that C 2 equals to b square. So, finally, we can write our equation as xi square equals to minus 2 n delta square by k f 1 plus delta into x square by 2. So, 2 cancels minus q f delta square by k f 1 plus delta x plus b square, or xi square minus b square, this is minus delta square by k f 1 plus delta, this is 2 q f naught plus n x into x. If we have recharge is equal to 0, then n equals to 0 and we can get a simplified relationship with n equals to 0, and if we have xi equals to 0 at x equals to L, we can get this is b square equals to delta square f 2 q f naught plus n L into L. So, again we have found out one relationship between depth of this phreatic aquifer from ocean surface to impermeable bottom. Delta is the our Ghyben-Hergberg density relationship. Kf is freshwater hydraulic conductivity. Qf as we have defined in our assumptions, and n is the recharge rate, L is the length of the wedge. So, with this relationship we can easily find out the shape of the wedge, and this is the final relationship between different parameters in confined aquifer. So, we can utilize this thing for our calculations. So, we can conclude our lecture with this particular confined aquifer unconfined aquifer condition that we have derived here, and in the next lecture we will start with the case where we will try to find out the ocean island case, in which we will try to utilize the condition for symmetric radial flow conditions. Thank you.